Welcome to the NYNJPA weather education video for January 8th, 2014. First education video of the new year. And we're going to talk about lake effect snow, particularly what causes it and what can really lead to very heavy snowfall in the Great Lakes region. Now, of course, if you don't know, the Great Lakes are the following: Lake Superior, Lake Michigan, Lake Huron, Lake Erie, and of course, Lake Ontario. Now, I personally have some experience with Lake Ontario, as your meteorologist, Stephen DiMartino, went to Oswego, New York for college. That is basically one of the meccas for lake effect snow. And if you go towards a location called the Tug Hill and you want to see snow, this is a place to go, because this area in the Tug Hill region in western New York is one of the most prolific snowfall recipients in the nation, and it's just incredibly impressive the amount of snowfall that can fall in this area. So what causes lake effect snow? This is a diagram from the COMET program, which is a government sponsored program that teaches us about the weather, of the general lake effect snow machine. Here are the basic things you need. You have one large lake that is above freezing. So when they say heat and moisture, basically water temperature is above 34 degrees. And you have an Arctic or a polar air mass moving over that lake. Now, a couple of key points. One, the difference between the temperatures with the lake, let's say 34 degrees, and the air at, let's say, roughly 850 millibars, has to be 13 degrees Celsius. If you have that difference in the air temperature from the water to the air, then that is the benchmark to support the development of lake effect snow. Below that, you really don't see much development. Above that, the snow bands can become very intense. So the greater difference in the temperature from the lake to the air, the stronger the snow band. And in this case, and in this scenario, what you basically have is what's called a convective precipitation event, where you have warm air rapidly rising and interacting with cold air. That cold air is allowing that moisture to condense, forms clouds, and that moisture is called what's called upsloping, which is moving up against a higher elevation, basically from the lake bed up into, let's say, western New York or portions of the Chicago suburbs, or even in portions of Michigan and Ohio, around Cleveland. Obviously, the elevation's a little bit higher as you're moving away from the lake. So, as a result, you have what's called upslope, and it doesn't have to be dramatic, just enough to create some friction and enhance some lifting, and that's how you get your snowfall. So, basically, the idea here is that the longer the fetch, the stronger the temperature inversion, and, or should I say, temperature difference from the water to the atmosphere, and the better the frictional convergence, the stronger the snow band. But there's a little bit more to this than you would think. One of the factors that you have to consider when you're forecasting lake effect snow is whether or not the shape of the lake and the interaction between the water and the land, it could enhance the snow band. Now, in this case, what we have is Lake Ontario here. Notice the arrows here. This is basically the winds. What this is basically shown here is that there's warmer air over the lake and obviously colder air over the land. And what's happening is that warmer air is rising. Well, the air over the land wants to fill that space of rising air. So what you have here as a result is what's called convergence. Now, as a result, this convergence is usually focused on the southern side of Lake Ontario. Basically, the southern side of these larger lakes tend to get the heavier snow bands. So, as that convergence is becoming enhanced, this snow band, this singular snow band, becomes more and more concentrated and becomes stronger in time. So, as this enhancement develops, the potential for very heavy snowfall in portions of Oswego County, around Syracuse, up towards the Tug Hill becomes more and more impressive. Now, on the flip side, where you have convergence, you also have divergence, which is usually seen on the north side of the shore, which typically is Canada. So, in this case, what you have is a weakening of the snowband to almost nothing because what you have is a divergence of air at the surface. So when you're forecasting for these snowbands, it's important to take into consideration the influence of the land on these snowbands. And this is a perfect example of just that convergence setting up on Lake Ontario. So far we've been discussing mostly what's called the mesoscale feature of a lake effect snow event, which is small scale. But what about synoptic, large scale? What you really want to look for if you are interested to see whether there's going to be a lake effect snow event in your area is basically this type of upper level setup. This is the 500 millibar pattern as of last night, and you can see that there's a strong upper level low, in this case the polar vortex, basically setting up around northeastern Canada. Now what that does is it transports cold air from central Canada and northern Canada and the North Pole and sends that cold air down towards the Great Lakes. Meanwhile, this same pattern sets up an area low pressure generally to the north or northeast of the Great Lakes and a high pressure system either to the southwest, to the south, or southeast of your lake location. So basically what this does is set up a wind that creates a fetch over the Great Lakes. You typically want to see this type of 500 millibar pattern or an upper level low around, let's say, the St. Lawrence River Valley or around southern Quebec. That would lead to the transport of not only cold air, but keep the upper level and surface winds uniform from the lake all the way up to the upper levels of the atmosphere to create a stable, strong band of heavy snow. So when you see this type of setup on your weather map, that's when you know that lake effect snow will be capable in your area. But where is lake effect snow most likely to develop? Well, this is what's called our snow belts of the Great Lakes. And pretty much they are along the south shore of Lake Superior, on the southern and also the eastern shore of Lake Michigan, on the northeastern shore of Lake Huron, on the usually the southeastern or southern shore of Lake Erie, and on the eastern and southeastern shores of Lake Ontario. Now that doesn't mean that locations like Cleveland can't get lake effect snow. It just means that these locations are the most likely areas to seeing moderate to heavy snowfalls, and these areas typically see the most of their snowfall from lake effect development. In other areas, you're most likely to see this type of snowfall development via more like winter storms that we're accustomed to seeing on the East Coast. And of course, like I was talking about with the winds, where that wind fetch is coming from, like in this case from the southwest, determines what areas will be impacted. So you see with these arrows here, when the winds are from the southwest, which typically is not a significant lake effect snow development situation because that usually means warm air is being transported. But in some cases, this is the case where you have that southwesterly wind coming off of Lake Erie right into Buffalo and then right into portions of Oswego and the Tug Hill. Now, you also have winds that can come in from the west. Now, this clearly would basically support an Arctic air mass invading the region. Now, you have winds coming off the west, and it could impact portions of Ontario, in both cases, all the way up and down southeastern Ontario, but also portions of Cleveland, southwestern, or should I say northwestern Pennsylvania, and also much of western New York. Now, between here and here, these wind directions, you can get impacts where, for example, on Lake Ontario, your longest fetch, should I say, is a west-southwesterly wind that in some cases takes part of the fetch from Lake Huron, cuts it through Lake Ontario, and deposits a significant snowfall from Syracuse on north that could lead to snowfall amounts in the feet. That is pretty impressive. And of course, we have one more wind direction coming in from the north. Now, when this wind sets up, you better watch out in Chicago and in the suburbs around Chicago for very heavy snowfall, as this is a very long fetch cutting across Lake Superior and then down through Lake Michigan. And this type of snowfall orientation can produce some very impressive snowfalls over these locations to the south of Lake Michigan and to the south of Lake Erie. Now, one aspect to keep in mind is that different instability levels creates different types of snow bands. In this case, this is a sounding that would support multi-band snow. Now, what that basically means, let's go to a radar here, is that in this case, this is multi-band, where you have multiple areas of snow bands. They're not very strong, they're not very impressive, but they will be capable of producing a wide area of snowfall. They at times can reach heavy snowfall amounts, but generally are on the light side. Now, the reason why is that the mixing layer is not very deep. So the instability really is not all that impressive from the surface all the way up to the mid-levels. So the cloud tops, let's say the cloud base starts here, they can't really grow that high. So they're relatively low level cumulus clouds that develop off of the Great Lakes. So the snow bands are more diverse, and you get a little bit of difference in the winds as far as the fetch, and you end up with multiple snow bands. Now, when you want to look for one large strong band, that's when you see this type of mixing layer, where you have instability throughout the atmosphere. The snow clouds, the cumulus clouds, are able to build up through the mid-levels of the atmosphere, and you get one intense, very strong band. Now, notice the difference in the winds. In the multi-bands, you get some difference in the winds. You get what's called wind shear, and that leads to a dispersion of the transport of heat in the cold air. So the bands aren't able to concentrate, you have a lot of divergence and convergence, and you have a lot of instability in the atmosphere, leading to these multiple bands. In this case, the winds are uniform. Okay, so you have a deep layer, you have uniform winds, and this leads to a scenario of one solid, very impressive, strong band of snow that in this case, on January 12th, 1990, led to blizzard conditions. Now, where can we see that on the radar? How about right off of Lake Ontario? You have uniform winds, you have very strong instability, and you get this one solid line. Let's zoom in on that here. And you can see one solid, strong line of heavy snowfall. So to recap, lake effect snow is driven by the difference in temperatures from the lake to the air. When you get to that point where the difference is 13 degrees Celsius from the lake to 850 millibars, you get lake effect snow. The direction of the wind tells you where the snow band will develop, and where that wind sets up, well, the longer the fetch, in this case, off of Lake Ontario, the stronger the snow band. Further, the deeper the air mass is as far as the instability, the better chance you'll see a strong single band of heavy snow, provided that winds are uniform from the surface all the way up into the mid-levels of the atmosphere. When the winds are not so much in agreement, when you're seeing a difference from the surface all the way up to the mid-levels, even in this case, where it's not that terrible of a shift, you're basically going from north-northwest to northwest, there's still more likely a scenario setting up where you end up with snow bands that look more like this. where it's more scattered and you get multiple weak snow bands. So I hope you enjoyed this video and learned a little bit about lake effect snow today. As always, you can follow the latest weather information at nynjpaweather.com and nynjpaweather on Twitter, Facebook, Google+, and LinkedIn. Have a wonderful day and stay safe out there.